Hello and welcome to this EUSIPCO 2020 presentation on the paper Analysis of Phonetic Dependence of Segmentation Errors in Speaker Diarization. The authors are Simon McKnight, Aidan Hogg and Patrick Naylor, all from Imperial College London. My name is Simon McKnight. I'm a PhD student. Now, just a quick background on speaker diarization. It is to do with distinguishing speakers speaking at different times, usually on an unsupervised basis and often referred to as who spoke when. And there are various different ways of doing it. Most of the methods involve some form of feature extraction on frames, grouping features from multiple consecutive frames, and then clustering and/or labeling, and some resegmentation. But the most important aspect for this presentation is the evaluation and scoring methodology that is used. The standard scoring methodology that is used for speaker diarization was published by NIST around 15 years ago and hasn't really changed much in the last 15 years. And the scoring system is based on timing. So the diarization error rate is equal to the false alarm time plus missed speaker time plus wrong speaker time over the total speech time in a particular audio or a speech file. And that's been absolutely standard based on time for a long time. There are some standard relaxations that can apply to those systems, in particular forgiveness collars around ground truth boundaries and removal of overlapping speaker segments. The aim of this particular research is to note that in recent challenges, such as the Die-Hard challenges, forgiveness collars have been removed. And this, of course, makes sense because speaker diarization systems should rightly be evaluated on their entire performance. But the issue is that there is inherent uncertainty and subjectivity in the ground truth segmentation that could unfairly penalize systems that correctly estimate speaker segment boundaries. And before going into the main part of the research, we used a standard diarization system, DiaDK, along with the standard NIST evaluation software, MD-Eval, to compare how the diarization system performs when using the original AMI corpus files, which are less accurate than the refined ground truth segments that were later published by NIST as part of its rich transcription challenge in 2005. It's for the same meeting, but particularly an 11-minute segment of the same meeting, and is more refined. And we found that when using the original ground truth segmentation along with as the oracle and feeding the original segmentation into the DiaDK system, we got a fairly decent performance, 11.51% diarization error rate with a 250 millisecond forgiveness collar compared to a 21.26% diarization error rate with no collar. And then, unsurprisingly, when we used the refined segmentation for both the scoring and the input into DiaDK, we found a couple of percent improvement in the system, 8.79% with a 250 millisecond collar, 20.23% with no collar. But then we tried using the original segmentation into the scoring and the refined segmentation into DiaDK, and we found here that despite the fact that the system was using a better segmentation, the results were considerably worse than otherwise, 19.39% with 250 millisecond collar and 29.14% with no collar. And this really led us to investigate how important the uncertainties around these AMI corpus collars, and in particular, we investigated the phoneme dependence of the uncertainty. And This slide shows in particular the differences in the segmentation. The first red line, looking at the original segmentation, we can see that for somebody saying one sentence, which was before the meeting, and that we have to keep in mind as we're creating this, the original segmentation did not have any gaps, even though there was a bit of a pause in what someone was saying. The more refined segmentation did show a bit of a gap. So although somebody was saying the same sentence for the whole time, it was treated as separate utterances in the more refined segmentation. Now, looking at the AMY corpus as a whole, we evaluated the phonemes that were available over the whole corpus, finding that when looking over the whole corpus, regardless of where the phoneme appeared in the audio files, there was, well, some phonemes were clearly more common than others, R and T being the most common phonemes. But then when we looked at phonemes that occurred at the start of utterances and the end of utterances, we found things to be more extreme. Some phonemes occurred far more often at the start of utterances than others. Y and R appeared a lot at the start, whereas at the end of utterances, the same thing occurred, and we saw R and T appeared quite a lot at the end of utterances. So that led us to think, can we take advantage of that in devising perhaps some phoneme-dependent collars? And we started looking at phoneme durations and thinking, well, if there was some uncertainty at the start or end of an utterance, perhaps we could use a standard form of duration of the phoneme to feed into a forgiveness collar there. But the problem there was when we investigated the lengths of phonemes at the start and end of utterances, we found that there was a huge variation, as can be seen in these two graphs, both at the start and at the end. So this variation was too great to be able to provide any certainty or confidence that we could use phoneme duration to determine what the forgiveness collars should be. We also tried looking at the AMY corpus to identify where start and end phonemes were, and this illustrated another problem that we had with our particular chosen corpus. The problem was the segmentation did not exactly correspond with the phonemes, and so when we were trying to identify whether a particular phoneme occurred at the start of an utterance or at the end of an utterance, we searched through the phonemes to find phonemes that where the ground truth segmentation said the utterance started. We then tried to find the phoneme that had a starting SIL, SIL, which was for a longish silence, followed by a phoneme, and at the end we have a phoneme followed by SIL. But we found even identifying these start and end phonemes based on the standard segmentation was problematic, as these graphs show. So the top graph shows, well, the beta lines are for each individual meeting and showing that for a particular duration time. So the x-axis shows the time between the Oracle ground truth segmentation and trying to find the phonemes, the utterance start or end phoneme, making that collar wider. Even when we extended it to 500 milliseconds, we were only finding about 70% of the phonemes at the starts of those utterances, and similarly for the ends of the utterances. In the top graph, the dashed red line is the average over all meetings, and in the second graph, it's a dotted purple line that shows the average over all meetings. The final graph simply shows those two average lines from the first two graphs to illustrate more clearly the problem that we had in identifying those starting and ending phonemes. Um, and then with the AMI corpus, because the AMI corpus has a large number of files, it has 163 meetings with phoneme information. So we were able to do quite a lot of information analysis on those files, but there are only one or two files where we have more accurate segmentation available. One example is this AMI 2005-0204-1206 segmentation that was made available as part of its transcription challenge. And unsurprisingly, when we did the same exercise of trying to identify utterance, start and ending phonemes, with the more refined segmentation, we got a much better hit rate, but this was only for one particular file because we didn't have more information than that. But quite quickly, you can see that a 90% hit rate was achieved. So ideally, if we'd had more refined segmentation for all the files, that would give us better result. But the cost and effort of doing this manually is extremely problematic. We then tried looking to see whether we could quantify the uncertainties, so at the start and end phoneme, which are the distances from the ground truth utterance boundary to the starting and ending phonemes. Now these graphs, the top two graphs look at the starting phonemes, and so the top one is starting phoneme mean distances, and the second one is standard deviations, and then the second two are the ending phoneme means and standard deviations. And we can see that there is considerably more uncertainty with the ending phonemes, how long they last, which is intuitive because when somebody is speaking, you'd normally expect them to have some uncertainty leading into a sentence, and perhaps a sentence at the end would tail off. Yet during the sentence, people would speak more quickly. So the fact that these uncertainties arise make it very difficult to quantify what phoneme duration we could use as an oracle standard. But the fact is that some phonemes do lead to longer uncertainties than others, so it would be possible to develop some system where we could have forgiveness collars depending on particular phonemes. And that leads us to our conclusion. This research has shown there is considerable uncertainty in determining exact start and end utterance times for speaker diarization systems, and that can lead to inaccuracies and ground truth segmentation that unfairly penalizes speaker diarization systems that correctly determine when utterances should start and end. And we do think this needs to be taken into account in evaluation tools. It's all very well to remove forgiveness collars altogether, but it would be better to have something that can take into account what is at the start. But we need to take into account we need to determine utterance boundaries in a consistent manner with the start and end phoneme times, perhaps distinguishing important errors from less important ones. And if we can do that, it might be possible to introduce reliable phoneme-dependent collars. And that brings us to an end of this presentation. Thank you very much for listening, and do send us a message if you would like to follow up on anything.